campfiring. Come on, Whip. Oh, I don't know why my webcam is not displaying currently, but I'll have to troubleshoot that later. All right, any questions before we get started on anything? So don't forget the RCC scholarships. I think there's flyers everywhere. But RCC has like their own in-house scholarships through that RCC Foundation. So maybe you've seen the posters around campus today. And so the deal is they have extra money and less students have applied so far than in the past. So if you haven't done so already, apply for that money, get those scholarships so you can help pay for your education. And then, so I know I'm behind on grading, so trying to catch back up. So lab 4 should be graded. And so check your grades. Some people have like mislabeled the labs in Gradescope. And if that is you, if you could just like email me, especially if you notice like you have zeros in there and if they've kind of been there for a while, just email me all the lab reports because that'll be easier than me trying to like go through Gradescope and match up like random labs with the right one.
Is Gradescope different from Blackboard?
Yes. Yes, so Gradescope is where I have people, especially the online students, turn in like the exams and then all the lab reports. So those are the only assignments on Gradescope, and then everything else is through Blackboard. And so other missing assignments, again, just get those in. So finish missing assignments, because that is what will hurt your grade, is the zeros rather than anything else. All right, so let's start chapter 7. So with Chem 104, we move pretty rapidly, so we're already switching topics. And so we kind of have looked at this before. So we've looked at the different states of matter, of solid, liquid, and gas. And so if you recall, solid has a fixed shape and fixed volume. And you can see that from the world around you. All these solid objects, obviously they don't change shape. And then liquids, so of course you all drink liquids, handle liquids, you know that they have a fixed volume but take their shape of the container, and we talked about how molecules can just slide past one another with those intermolecular forces. There we go. And then for gases now, they're even further apart, and so now we have no fixed shape, right? No defined volume, and so we mentioned that gases are compressible. And so again, you probably have seen this before. Like if you get your tires filled up with liquid nitrogen, you take it down there, so they have a huge tank, and it's nitrogen compressed all the way down to a liquid, and then you open it up, and of course, you get gas coming out of it. So let's now focus on gases. So this is our gas chapter. And so we know that gas is a phase of matter, and this is a phase composed of particles that are moving randomly and very fast in their container. And then so we'll look at now the kinetic molecular theory of gases. So we're kind of giving this a more idealistic treatment. And so we're saying that gas particles will move in straight lines until they collide with either the container wall or another particle, then they bounce off. And so in this case, we're kind of ignoring intermolecular forces. So So, right, we don't care that they go past near a molecule and they would be attracted to one another. So we're kind of ignoring that. We're also kind of ignoring the size of our particles. So just, again, an idealized treatment. So also assuming elastic collisions. So not losing any energy. And then so we get this idea of pressure then every time an atom collides with a surface. So then that is called pressure. So you can think about this with a balloon. And so you inflate your balloon, and so you have to put a bunch of air inside. And of course, for it to be inflated, those molecules have to be exerting enough pressure against the atmosphere. So of course, the atmosphere, there's a bunch of air molecules, and they would be colliding on the outside of that balloon, trying to smash it back in, were it not for the counteracting force of the gases inside, keeping it inflated. And so that means that molecular collisions are pressure. And so we can see that if we relate it back to this formula here. So pressure is defined as a force exerted per unit area, and then in this case by gas molecules as they strike the surfaces around them. So pressure is just force over area. And so again, that gas pressure is the result of all the collisions of those gas molecules as they hit the surface. And of course, the pressure depends on how many gas particles or how many collisions you have, the volume of the container. So we can see we have it over this area force. So if you have a smaller container, right, same amount of gas molecules will be concentrated, so there'll be a lot of collisions. Whereas if you have a large container, then those gas molecules will have less collisions per area. And then we also have the speed being a factor, so how fast they're going or how slow will also, of course, dictate the rate of collisions. And so, like we were saying with our kinetic theory of gases, the collisions are said to be elastic, meaning no exchange of energy occurs. And so in the real world, they would be inelastic collisions, so you would lose a little bit of force, but we'll kind of see where the discrepancies arise. So some common units of pressure, it's either going to be given in probably millimeters of mercury, torr, or atmosphere. And so here's a little barometer. So how this works, you have a pool of mercury, and then you have this glass tube that's under a vacuum. And so you can imagine, right, all the molecules of air, they're colliding down on top of the mercury, doing a bunch of collisions. So the force of those collisions drives the mercury up into the glass tube until it reaches the height associated with whatever pressure. And so in this case, what's being shown here is 760 millimeters of mercury. So that's how tall this would be, measuring from the base to the top of the meniscus there. And so that's the same as 29.92 inches. You might see inches, let's say if you look at your local weather station, I'll give it to you in inches potentially. Or this is also 1 ATM. So these are the conversion factors you'll want to know or write down somewhere. So millimeters of mercury is the same as torr. And so 760 millimeters of mercury equals 760 torr, which is equal to 1 ATM. And then there are other units of pressure as well that may come up. So you may see pascals, which is Newton per meter squared. And so this is equivalent to 1 ATM, so 101,325 pascals. You might also see kilopascals, so that would be kPa. And of course, that just means that you would move the decimal point over to give you 101.325 kilopascals equals 1 ATM. And then, so we have pounds per square inch. You might see this on your tires. So typical tire pressure is around 33 PSI or so, at least for a car. And then, like we mentioned, we have torque, so 760 torque, 29.29 inches. If you see bar, so you may also see bar if you look at your local weather station. So 1.013 bar is equal to 1 ATM. And then, of course, ATM. And so most of the time, and I'll point out when it's okay to be in other units, but this is kind of your safest unit. So ATMs will kind of crop up in other areas, and we also have the combined ideal gas law, which we'll discuss. But this is going to be the unit that you want to be in. So now we'll look at how to characterize our gases so we could determine the pressure. And so like I mentioned, ATM is kind of the common SI unit, then volume, and then it will be measured in liters as our common unit. And then temperature, so this is also really important. So if you kind of recall back to temperature and what the Kelvin scale is based off of. So now we have to have it make some thermodynamic sense when we do these equations and relationships. So we can't have negative temperatures. If, let's just say we're in Celsius, right? That doesn't work out thermodynamically, doesn't check out. And so we would want to be in Kelvin. So I would start this, whatever you need to do, because this is really important. And this is probably the most common mistake that students make is they forget to convert from Celsius to Kelvin or something like that. And so just a little recall that the temperature Kelvin is just equal to your temperature Celsius plus 273, or 273.15 if you're feeling really precise. And then we'll also relate it to moles, and that's just given here by our symbol N, our little n there. And so we'll see that these properties are all interrelated. And so this means when one changes, it can affect the other. And so first, we'll look at the simple gas laws and then kind of sum it all up in our combined gas laws. And so this is just where we're going. So we'll look at Boyle's law, which it relates pressure and volume. Then Charles's law next, which relates volume and temperature. And then we'll look at Avogadro's, which relates our molar amount and volume. So Boyle's law, what they did is Boyle and Hooke here use a J tube to measure the volume of gases at different pressures. And so they trapped a sample of air in a J tube and added mercury to increase the pressure. And then so they noticed an inverse relationship between volume and pressure. So inverse meaning if volume increases, then pressure has to decrease, or vice versa. So if pressure increases, that must mean volume is decreasing. And so looking at our little piston system here, we can compare our initial conditions with our kind of second scene. And so we start off 1 ATM, volume is 1 liter, and we have a little weight here. So we increase the pressure, so now we're at 2 ATM on pressure, and so that means our volume is then halved by that same amount. And so again, Boyle's law states that the volume of gas is inversely proportional to pressure. And of course, decreasing the volume forces the molecules into a smaller space, and gas particles would collide more. So we're shrinking our space down more and more, compressing it. And then of course, what accounts for this behavior out here kind of levels off. Yeah.
It requires more energy to compress it.
Maybe think like more simply, potentially, or think about what you're kind of doing. What's the limitation, I guess?
Oh, well, I mean, eventually you'll just compress it so it becomes a liquid or a solid.
Exactly. So
And then
eventually,
you can technically compress it more, but not really.
yeah, once you get, I mean, once they're now like touching, you can't really compress it any further. So that's where that leveling off comes in. And so now we have kind of our relationship and equation that we're interested in. So we know that pressure times volume always remains constant. So therefore we get this relationship of P1 V1 equals P2 V2. And so if you're using this formula, so units of pressure and volume do not matter as long as they are the same. So we could do torr and torr, milliliters and milliliters. It doesn't matter, you just don't want to mix them up, right, of like milliliters, liters, and ATM and torr. That would give you a disaster. So this one doesn't matter so much, just be consistent with your units. And so now we can kind of think about the relationship with diving. Has anyone gone diving in here? Oh, you've gone diving? Oh, 2 people have gone diving. Anyone in the chat? So what do you have to do when you dive, when you go back to the surface?
You have to wait, like the pressure to adjust essentially.
So,
Yep.
so either wait or go up really slow. And so do you all know why you have to do that? Do they?
Well, because the nitrogen bubbles in your, sorry.
Oh, I'm just giving the explosion.
Yeah,
Usually explode.
Well, the nitrogen, well, the bubbles in your blood get like dissolved. The air in your blood gets like dissolved, I believe it is specifically. And then like it can expand into bubbles causing like blood clots if it's done too quickly.
Yeah, exactly. So excellent answers in class. I like the explosion. But exactly.
Explode. You may, however, have an aneurysm.
That's pretty close to as exploding as people do, I guess, unless of course, other means of bomb. Yeah. So exactly. So now we're seeing kind of the effects of Boyle's law in real life. So we're at a depth. So you're diving, you're down at a depth of 20 meters, so that's 3 ATM of pressure. And just to recap, so everybody, in case you couldn't hear, and so we have, of course, gases dissolved in our blood and our body, and if we were to rise too quickly and not give the pressure time to equilibrate and move slowly, then, of course, we can have this rapid expansion of gases, which can lead to bursting and everywhere that we don't want it to. I mean, even in just, the lungs. So if you decrease the pressure by a factor of 3, then of course the volume just in your lungs would expand by a factor of 3. And of course, always exhale while rising. And we'll add and go slow. So safety tip of the day. All right, so let's do a little practice problem. So as you breathe, you inhale by increasing your lung volume. A woman has an initial lung volume of 2.75 liters, which is filled with air at an atmospheric pressure of 1.02 atm. If she increases her lung volume to 3.25 liters without inhaling any additional air, what is the pressure in our lungs? And don't forget I'll rewrite your formula. So P1 V1 equals P2 V2. So I'll give everyone a minute or so to solve it. We'll go over it. And do we have an answer? I see one in the chat. What do we get?
0.863 ATM.
And chat is telling me that they agree. And so let's just go over it together. So we just have to determine who's P1, who's V1. So we have our initial lung volume, so V1, our pressure, P1, and then our new V2. And then so it doesn't really matter what units we're in, but we're in consistently liters, liters, and ATM. So just plug everything in now. And looks like everyone agreed, 0.863 ATM. Any questions on that one? You want to see anything worked out? Or?
How did she increase the volumes of her lung without inhaling any additional air? I feel like
Your diaphragm, it moves down, and that's how your lungs.
But I feel like having a lower ATM would cause some serious damages. It was,
Well, you know, if you could
That's-
create a vacuum, but
that's,
obviously this is like a little idealized scenario.
Seems like it would be really unhealthy for the person.
Well, just assuming that if you were to, you know, move your diaphragm muscle down without opening your mouth or nose somehow. But, all right, excellent job on the math there. So now let's look at kind of our next relationship. So now we're looking at volume and temperature. And so now they have a direct relationship. And so the volume of a fixed amount of gas at a constant pressure increases linearly with increasing temperature in kelvins. And the important thing to add to here, this is while keeping pressure constant. So that's the thing about these little relationships, is you're only changing these two variables and everything else should be constant. So your pressure is constant, your moles are constant. So we're not doing anything, just relating volume and temperature. And so this kind of makes sense. So if we, according to our kinetic molecular theory, so we're increasing the temperature, that means that the average speed then and kinetic energy increases. So then if we have increased kinetic energy, that means increased collisions. And so we need that greater volume to spread the collisions out over a greater surface area so that the pressure is unchanged. And then so we look at this graphically. And so again, this is where it's important that we base it off our Kelvin scale for this relationship. So it wouldn't make sense to have a negative number here. And so we can just see, again, our linear relationship as temperature increases, our volume increases. And then, of course, eventually our gases condense and become a liquid. So this trend kind of falls apart, obviously, when that phase change occurs. And so looking at this in the molecular view, so again, our temperature increases. That means our gas particles move faster, the collisions are more frequent, and the force is greater. And so, of course, the only way for the pressure to remain the same is for that gas to occupy a larger volume. And so same concepts, if you have a balloon and it's moved from ice water to boiling water, so it would be small here, low kinetic energy, and then move it over to boiling water. Now that it would expand as those molecules move faster. And so let's actually look at a video. if I can find the one. There we go.
Hi, everybody. I'm
Up our volume.
meteorologist Jay Birschbach along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. And I just want to give you a sense for how strong,
Okay.
how rugged these barrels are. Jay, if you could stabilize the barrel, I'm gonna take a sledgehammer and try to. If you relied on me to crush this barrel, we'd be here all day.
Sure.
Because that thing is pretty tough. So instead, like you said, we're gonna use air pressure to crush this drum. So
All
let me
right.
flip this up. I'm just gonna stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside, about 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now, water vapor, when it's warmed up, and air, when it's warmed up, occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up.
Okay.
So help me flip this up on
All
our
right.
stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
Right. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with.
One at a time, yeah.
Okay, I think you can see there's a good sort of jet of steam shooting out, but we're going to try to capture that
Okay.
by putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. I'm going to spin it down. Rotisserie. Well, the first thing we should hear are a couple of the ends of the drums popping in.
There we go.
A couple of the ends going in. There's the other end.
There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum. And because that water vapor inside and that warm air inside
There it
has
goes.
cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is
to the drum.
amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can. Or if you've ever rinsed out plastic milk jugs,
Sure.
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Sure. Yeah, no one, having that blowtorch,
blowtorch is
for the
probably
experts. Experts like you, exactly. Well, this is really neat. A real 55-gallon steel drum crushed
Still going.
like it's made of thin aluminum or paper or plastic.
All right, so you get the idea, right? Similar concept, they just went the other way. And this time, of course, they trapped that gas, so below kinetic energy. And of course, the atmospheric pressure pushing down on that 55-gallon drum caused it to collapse. All right, so let's do a little practice problem. And so don't forget our formula. So now it's a little bit different in the sense that they're over one another since they have a direct relationship. So that means V1 over T1 is going to be equal V2 over T2. So now see if you can try our practice problem. So sample of gas has a volume of 2.8 liters at an unknown temperature. When you submerge the sample in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. So what was the initial temperature? So I'll give everyone a few minutes to try it before we go over it. I'll rewrite the formula. So V1 over T1 equals V2 over T2. We have answers. See people punching stuff in. See answers in the chat. So we had our V1, we don't know T1. And then we have, so T2 and V2. But then, so what's the trick with T2 here? What do we need to do before we do anything?
Convert it to Kelvin?
Yep, so always want to be in Kelvin. So our T2 is 273 Kelvin. And so now it looks like we can plug everything in. So 2.80 liters. And in the chat, just a reminder, so you add 273 to your temperature Celsius volume to get there over T1. So trying to solve for T1 is equal to 2.57 liters over 273. And so what do we all get? Just waiting for chat confirmation. There's somebody in class. Did you get an answer?
I got 0.0033.
Other people get that? Looking for consensus. So let's see. 273 times 2.8 divided by 2.57. So I see I get 297 Kelvin, and I see that in the chat. So what other people got?
So you did 273 times 2.8
Yeah.
times those two.
Yeah, so you do cross multiplication, so 273 times 2.8, and then divided by 2.57 to get x. So then in Celsius, we have to just subtract 273. So then you should have gotten 24. Is that what you got? Did you punch it in? Test it out? So make sure you punch it in, test it out yourself. Never know what could go wrong. Oh, I lost my, here's my marker. So we have 297.4 Kelvin or 24.4 degrees C. And don't forget, Kelvin doesn't have a little degree sign, and Celsius and Fahrenheit do. And now our last kind of little relationship here.
Avocado's law.
Yeah. Avocado.
Avocado's law.
Funny story. We were doing science test for it, and the prize was an avocado with Avogadro's law, like toothpicked into it. And this was like right before, like we're going to take like a 2-week thing for COVID. It turned into a lot longer thing. So I put it in like one of the football helmets in the computer lab. Because I will let you know that my teacher actually told me to do that. Like the block class teacher told me to do that. And it stayed there intact for all over the summer.
So was there like a rotten, smelly avocado later, or did it
Honestly,
sprout?
no, it mainly just shriveled up.
Oh. I'm trying to, there we go. That looks more like an avocado person. All right, so Avogadro's law. Now that we all have avocados on the mind. So now we're just looking at the relationship of volume and moles. Again,
Toast.
keeping everything constant. So volume is directly proportional, once again, to the number of gas molecules when pressure and temperature are held constant. And this makes sense. And so obviously if you're putting more moles of gas, you're blowing more molecules of air into something. If you want your pressure to be constant, then you have to, of course, expand the volume. And, oh, this is the other really important thing. So equal volumes of gases contain equal number of molecules. So again, the identity of the gas doesn't matter. Doesn't matter whether it's helium or xenon, just equal volume contains the same number of molecules. And we'll come up with another relationship later. We'll just hang on to that thought for now. And then so this gives us, so anytime they're directly related, you can see the formula is going to be in this form where they're on top of each other. So V1 over N1 is equal to V2 over N2. And so your units of volume don't really matter, again, as long as they're consistent between one another. And I don't think you can really have moles in another way. And so again, we see as our volume, or rather as N increases, then our volume must also increase if we're holding everything else constant. And so, of course, if we increase the number of gas molecules, that causes more collisions. So we have to increase the volume to keep it spread out over an area. So let's see if we can try our practice problem. So I'll rewrite our formula. So V1 over N1 equals V2 over N2. And so we have a male athlete in a kinesiology research study has a lung volume of 6.15 liters during a deep inhalation. At this volume, his lung contains 0.254 moles of air. During exhalation, his lung volume decreases to 2.55. And so watch what the question is asking. So how many moles of gas does the athlete exhale during exhalation? And of course, we're assuming constant temperature and pressure. So I'll give everyone a few minutes to work through it, then we'll go over it. So we have, looks like we have 3 sig figs in all these numbers. So it looks like chat has a consensus. You have an answer. 0.105, or is there any chance you like swapped numbers on there? Well, let's go through it together and see what we all did. Sounds like you're close, but all right. So we have our initials, so our V1 and our N1, and V2. And so how many? So first, we need to determine how many moles remain. So just start plugging everything in. So it's equal to 2.55 over x. So cross multiply, so 2.55 times 0.254 divided by 6.15. Oh, so this is the answer you got. So that's x then. So that's moles remaining, right? So 0.105. So that's moles in lung. And then so to get moles exhaled, and that's the tricky part of this question, is it was asking the exhaled. So you take 0.254 minus that answer, and so you should have gotten 0.149 moles were exhaled. So excellent job, chat. Did everyone get this in class? So at least hopefully you made it to this part, figuring out how much was in the lungs, and of course the last step was just trying to recognize the little trick there. All right, so now we have our ideal gas law. And so this ideal gas law is really all you need to know. So if there's one formula you need, it's this one. So PV equals nRT. And then, let me look at the homework for a second. So we're going to just derive, oh, this doesn't have the one of the combined gas laws that I was looking for. All right, so I'll explain what I was looking for in a second. So let's do a little derivation. And so we are given this overall expression. So again, PV equals nRT. And so let's define everything. So our pressure is going to be an ATM. So this is where all the units matter once we use this ideal gas law. So pressure is in ATM, volume is in liters, and of course is our moles. And then this R is this 0.0821, and that's for moles, liters, Kelvin, ATM. Because if you were to look it up, you could look up gas constant, and there's a whole bunch of different gas constants depending on your unit. So you want this one, again, 0.0821, and then temperature in Kelvin. And so let's do a little derivation, how we can get our formula out. So we start with PV equals nRT, but R is just a constant, so it's just a number. So now we could rewrite this as PV, and I'm just solving for R now, divided by N divided by T is equal to R. And so let's say I wanted to look at another set of conditions. It doesn't matter what it is. So now this is equal to P2 V2 over N2 T2. So again, they're both set to R. So now this gives us what I like to call our combined ideal gas law, which would be P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so now you can see where the other individual laws came from. Now if we kind of look back at them. So we said Boyle's law was relating volume and pressure. And so again, that means that we'd be holding N constant and T constant. So for Boyle's, right, we get back our P1 V1 is equal to P2 V2. And so we could do that for all the rest. So Charles's, now we're holding our pressure in moles constant, so just looking at volume and temperature. So pressure in moles, that would all cancel out to give us back our Charles's law. And then of course we could also get out Avogadro's as well, so just looking at moles, volume, so holding pressure and temperature constant, so everything cancels to give you back out, again, our individual laws. And so you might also see, so something that comes up is just this like combined gas law. And that's what I thought was on your homework. And you might just see it. And so the relationship that you may see given to you is P1 V1 over T1 is equal to P2 V2 over T2. But you see that's basically the same thing. It's just now holding moles constant. And so that's all I really want to emphasize to you, is that either this form or this form are really the only forms you need. Then you can cancel out whatever other variables are held constant, and then you get whatever formula is appropriate for your situation. So the other thing that's pretty useful, so let's say you had trouble remembering who's direct, who's indirect. Well, we set up our PV equals nRT again. So notice, what do you notice about pressure and volume? So they multiply, right? So that means they're on the same side. And then did we say, were they inversely or directly related? Do you remember?
Inversely?
So inversely. And so now we can remember that because, okay, if they're multiplied together, they have to equal this constant. So that means if one goes up, the other has to go down. So you can remember that. So inverse. So anything that's inverse will be on the same side. And then now all our things that had that opposite, or, excuse me, direct relationship, meaning that they're on opposite sides. So now that makes sense. So pressure and temperature are on opposite sides. So of course, if pressure goes up, that means that this whole thing is going up. So temperature is going up. And so that would mean that they're directly related. So opposite sides of our equation. So now we know they're directly related. We can tell our volume in moles are also directly related since they're on opposite sides. And we could do temperature and volume would also be directly related, right, if we're holding everything else constant. And moles and temperature would be inversely related since they're on the same side. So if you were to hold pressure and volume constant, which might be a little funny, then you could keep everything constant if you increase the moles and decrease the temperature, or vice versa. So does that make sense? Hopefully, useful tricks. And so this is just re-deriving out everything else. So now let's do a practice. So calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atm and a pressure of 315 Kelvin. So what formula do we want to use?
Can we just use the PV equals RT?
Yep, so let's do that one. So PV equals nRT. And so pressure's already in ATM. That's good. I see it in the chat too. We're already in moles, so we just need our R, so 0.0821. And so we're trying to solve for volume. So we could.
Wait, what's R stand for again? I can't remember, sorry.
It's just a gas constant, and it's when you have the units of moles, ATM, liters, Kelvin.
Okay.
And so now just rearrange. So nRT over P. And so what do we get in the class? So 15.95, is that what everyone else got in class? Again, I see nods, and then chat had chat consensus as well, 15.95. Excellent. Y'all are flying through this chapter. Any questions on that one?
How is the ideal gas law or the R value calculated?
I'm not exactly sure how that one was derived. I'm sure that at one point they, had to figure out all the other quantities and then solve for R, like if you had volume, moles, pressure, temperature.
Okay, that makes sense.
But I'd have to look it up, like, exactly how they got, like, an exact figure. All right, so let's see how far we get with the rest of this. And so now we have this thing called standard conditions. And so you might see this in like a word problem, for example. And so they would be abbreviated by STP. And so standard conditions just mean you're at 1 atm, 0 degrees Celsius, 1 mole of substance, and then our standard volume, and this might go back to your N question, or excuse me, R question, how they got that. But they determined that the volume of 1 mole of substance at this condition is 22.4 liters. So I would highlight that, circle that, because that is extremely important. And so all they did, they just plugged it in to here. Let's just type it out so we're all on the same page. So solving for volume STP, so 1 mole, so 1 times our gas constant times our pressure, and sorry, I screwed that up. So 1 times 0.0821 times 273 divided by 1 atm. So that gives us that 22.4 liters. So again, that's just our molar volume. And so this also means, right, that 6.022 molecules of gas occupy this 22.4 liters. And so even though, again, these are different types of gases, so we have helium, which is the smallest, still 22.4 liters. And we have xenon, so one of the larger gases, 22.4 liters, compared to methane. So now covalent compound, same thing, 22.4 liters. So don't forget that. So the standard volume is at, yeah, the 22.4 liters. And so I didn't write down a practice problem, but we should. And so something that's kind of tricky that will come up is that word problems will kind of want to make you use proportions, and that's going to make your life easier. So you could say, what volume do 4.78 times 10 to the 23rd molecules of propane occupy at STP. And so we'll just kind of work this one together. You could do the whole conversion, right, molecules to moles, and then do now our new conversion factor, since we know, again, at STP, 1 mole is equal to 22.4 liters. So we could write this, again, either way. So depending, right, which way you're going, you need to pick your appropriate conversion factor for your dimensional analysis. Or it might be easier to just kind of skip that step and kind of use our molar relationship and our Avogadro's number. And so what you could also do is, well, I know 6.022 times 10 to the 23rd molecules occupy 22.4 liters, because again, that's just our STP definition. So then we could set up our proportion. So then if I have 4.78 times 10 to the 23rd molecules, and I want to know the volume, then I can solve for x. And so that works out. So now let's just solve it. So 22.4 times 4.78 times 10 to the 23rd divided by our Avogadro's number. And so that means that this amount of molecules occupies 17.78 liters. So anytime you can try to use a proportion too to simplify the math in your life, feel free to do so as well. Alright, so now let's look at Dalton's law. So all Dalton's law is stating, this is pretty simple, it just says the total pressure of a gas mixture is equal to the sum of the partial pressures. So again, the particles of different masses, we don't care, we're assuming that they don't interact, so it doesn't matter. So we're not having to account for intermolecular forces or anything. And so all this means is, again, gases behave independently. So our pressure total will just be your component of A plus your component of B plus C, etc., etc. So you could rederive it from here, so based off of the number of moles, if you needed to. So the other thing is then you can relate your mole fraction. So your mole fraction is just the ratio of the partial pressure a single gas contributes. So that's equal to its mole fraction. Here we go. I was looking for an example. And so we can, the number of moles of a component in a mixture divided by the total number of moles is the mole fraction. So moles of your component over total moles gives you your little mole fraction there. And so this means that our pressure of our component is equal to our mole fraction times our pressure total. And so this means, so now we actually have some numbers. We can put some sense to these variables. And so we know we have air, so our air is at 1 atm, so that's just the pressure. And then so if we know that nitrogen makes up 98% of air, we can go ahead and find its partial pressure. So this is just its mole fraction, and so now we can take 0.78%, so convert that to a percent, so 0.78 times 1 atm means that the pressure of nitrogen in our ambient atmosphere is 0.78 atm. And so you could do this for all the main components of air. So these are just kind of the main three here. So oxygen is 21% of the air, if you were to look at the composition. So you can just convert that, so 0.21 times 1 atm gives us 0.21 atm. Argon, so you can tell that's a trace amount, so 1% composition of air, and so that would translate to 0.01 atm if our pressure total is 1 atm. Let's see. probably save the rest of this for Thursday. That's a good stopping point. Yeah, so any questions on gases so far? And, sorry, which part? And the last, this one? This was just solving for volume at STP conditions. All right, we'll go ahead and end lecture a little early. I'll stick around on stream as usual. And then I have the lab for today out if people want to grab it. Otherwise, I'll have it out at 7 for y'all.
I was wondering if you could walk me through a question from the lab 6 on theoretical yield and percent yield.
Yeah, I could do that on stream too, since it's probably cropped up a lot. Oh, I was just trying to find a lab just in case. Yes, which one?
It's lab 6, and it was question, at the end of the lab, it was question 3. It was to use the balance equation to calculate theoretical yield and percent yield.
So, number 3 there. All right, so what did you get for your, like, what was your ratio of magnesium sulfate to water?
1 to 7.
So, and you could have different numbers. So it could be a 1 to 7. I think that's the proper answer. Most people end up getting like a 1 to 6 ratio. But then we just want to start by writing out our formula. So that's what you did in the first part. So I was doing that. So magnesium sulfate complex with 7 waters. And then if we liberate that, that gives us anhydrous magnesium sulfate plus 7 waters. And then it says calculate your theoretical yield. And so there's a couple of tricks for this, and I'll do them both. So what I've been telling people is first you have to find the molecular weight of this. And for your case, it could be individual. So again, some of you may have 7, some of you may have 6, etc. You could have 5, but it should be some nice whole numbers. So find the molecular weight of that. Then we also need the molecular weight of our anhydrous. Does anyone have that by any chance? Just want to put some numbers. Okay. According to the internet, it says 120.366. Do you have a molecular weight for the hydrated one by any chance?
Wouldn't it, it's not the same?
No, so it would be then just 120.366 plus either, in your case, it'd be 7 times 18, since 18 is the molecular weight of water.
Oh,
And so in this case, again, I'm doing the 7 water
So-
ones.
plus the 7.
Yeah, so plus, so that's just for the anhydrous, plus your 7 waters, so that should give you 246.366 or something like that. And so what I've been telling people to do is start with whatever your mass was. So I think it was like 9 grams is what you started off with initially, like what you weighed out.
I think it was around there, yeah. I left my packet at home.
Yeah, so something like that. And then, so I was telling people to go like the full way. So 1 mole, 246. So that gives you moles of that. They're in a 1-to-1 ratio. And then, so once we get moles of magnesium sulfate, then we convert this back to grams. So that's one way to do it. So divided by 246.3668 or whatever. And then times 120. So we get theoretical yield of 4.39 or 7, or you could round to 4.40 grams. But the other way that I want people to start seeing, and maybe it'll become more apparent as we do more do more practice, so we can tell they're in a 1-to-1 ratio, right? And so something else we could do, we could just kind of skip and say, well, I know I have 9 grams of this compound that weighs 246.366 or whatever. And since they're in a 1-to-1 ratio, I can skip this. And I know that my new molecular weight of my anhydrous is 120.366. So I just have to solve for x. And so that would also give you the same thing. So 9 times 120.366 divided by whatever your mass of your hydrated component is. And so that gives you the same answer. So either way, I just wanted to show people the proportion so that if it starts clicking, you can kind of start moving a little faster, feeling more comfortable. Otherwise, just stick to the good old dimensional analysis, kind of step by step. So did that clarify? Yeah, and then so whatever you get for this, right, this is your 100% theoretical yield. And then so you have to take whatever you got on the balance and divide it by that to find your percent yield. So mass you weighed, so however much you're holding in your hand. At the very end, divided by our 100% yield, and that gives us our percent yield for that last part.
And that would be the 246 at the top there, mass weight.
Oh, this would be like whatever you got, like after you weighed
Oh,
your crucible at the end, so whatever
so
that
the
dried
9
mass.
grams.
Not the 9, but like the subtracted. It should be somewhere in like the 4 or the 3 region.
Okay.
I have to look at your paper. It should ideally be somewhere around 100%. It might be a little bit higher if you didn't quite get it dry. Might be lower, and of course your
I think
formula.
at home I was getting like 99%.
Yeah.
It's supposed to be close to that.
Yeah, a lot of people get it like close to that, or like a little over, a little under. Cool. Any other questions on the stream before I shut the stream down? It looks like chat is done, so I will stop streaming. Thanks again, chat.